Balance Training, Chapter 7, Part 1. Learning Objectives. Upon completion of this chapter, you will be able to explain the functional components of the postural control system in maintaining balance and preventing injury. Explain function and components of the postural control system in maintaining balance and prevention injury. Describe the role of balance training in improving sports performance and injury prevention. Identify the attributes of a progressive balance training program for athletes in any level of training. Introduction. Balance is the ability to maintain the body's center of gravity within its base of support, achieved through an interaction of active and passive restraints imposed by the muscular system, reflexive actions imposed by the peripheral nervous system, and anticipatory feed-forward control imposed by the central nervous system. This entire process is referred to as sensory motor control. Sensory motor control. I know sensory motor control, even for simple tasks, is a dynamic process that undergoes constant review, feedback, and modification based on the integration of sensory information, motor commands, and resultant movements. Optimum sensory motor control is designed to prepare, maintain, anticipate, and restore stability of the entire human movement system, postural stability, as well as each segment of the human movement system, joint stability. Balance is a component of all movement, regardless of whether strength, speed, skill, or flexibility dominates the motor pattern in question. For example, the relatively simple activity of sprinting is a highly complex movement pattern that requires losing, regaining, and maintaining balance on alternating legs, all in less than 1/10 of a second. An understanding of the postural control system, as well as the kinetic segmental chain about the lower extremity, helps conceptualize the role of the chain in maintaining balance and preventing injury. In the kinetic chain, each moving segment transmits forces to every other segment along the chain, and its motions are influenced by forces transmitted from other segments. The act of maintaining equilibrium or balance is associated with the closed kinetic chain, and the distal segment foot is fixed beneath the base of support. Changes along the distal kinetic chain can influence the efficiency of core or central components and position the center of gravity in either more or less optimal positions above the base of support. In other words, the coordination of automatic postural movements during the act of balancing is not determined solely by the muscles acting directly about one specific joint. Leg and trunk muscles exert indirect forces on neighboring joints through the inertial interaction forces among body segments. A combination of one or more mechanisms, ankle, knee, hip, are used to coordinate movement of the center of gravity back to a stable or balanced position when a person's balance is disrupted by an external perturbation. Injury to any one of the joints or corresponding muscles along the kinetic chain can result in a loss of appropriate feedback for maintaining balance. Balance training concepts. Postural control, page 245, part 1. Sports performance professionals must understand postural control and its components to efficiently and effectively train athletes to achieve optimal performance. The apparently simple act of maintaining an athletic position during sport is actually a continuing process of minute adjustments to keep the athlete's center of gravity over the base of support. The smaller the base of support, a single leg, the more precise and accurate the postural adjustments need to be to keep the center of gravity over the base of support. The postural control system integrates complex processes involving visual, vestibular, and proprioceptive inputs from the human movement system. Maintaining postural equilibrium requires sensory detection of motion and position in space, the resulting sensory motor integration, and the execution of appropriate musculoskeletal responses. It is proposed that balance and postural control are accounted for by two main neurophysiological mechanisms: peripheral neural mechanisms and central processing. It is proposed that maintaining postural equilibrium requires sensory detection of motion and position in space. The resulting sensor-motor integration and the execution of appropriate musculoskeletal response. It is proposed that balance and postural control are accounted for by two main neurophysiological mechanisms: peripheral neural mechanisms and central processing. Pro tip: it is important for the athlete to train for balance with the implement used in the sport, such as rackets, lacrosse sticks, baseball bats, and golf clubs. These implements become an extension of the human movement system and change the center of gravity. To sense its position relative to gravity and its surroundings, the human movement system combines visual, vestibular, and proprioceptive inputs through which sensory motor integration establishes balance. Processing occurs in the CNS within the brainstem and cerebellum. The appropriate motor program is then executed in response to the complex sets of sensory information sent to the central nervous system. These complex processes help produce optimal neuromuscular efficiency during functional activities. Page 246, neuromuscular efficiency. Neuromuscular efficiency is the ability of the neuromuscular system to allow the agonists, antagonists, synergists, stabilizers, and neutralizers to work together efficiently in all three planes of motion. Appropriate movement sequencing and efficient motor programs are essential for optimal performance and maintenance of structural integrity throughout the human movement system. Optimum neuromuscular efficiency requires integration of postural alignment, muscle balance, dynamic flexibility, core stabilization strength, multiplanar functional strength, and neuromuscular stabilization. Peripheral neural mechanisms in balance training. Peripheral neural mechanisms in balance training. Balance is a complex and highly integrated dynamic process involving multiple neurological pathways from constant sensory afferent feedback from a full array of mechanoreceptors, proprioceptive or somatosensory input, visual input, and vestibular input. Proprioception is the cumulative neural input to the central nervous system from all mechanoreceptors that sense position and limb movement. Kinesthesia is the conscious awareness of joint movement and joint position sense that results from proprioceptive input sent to the CNS. One more time. Kinesthesia is the conscious awareness of joint movement and joint position sense that results from proprioceptive input sent to the central nervous system. This position sense is largely mediated through the range of mechanoreceptors: muscle, joint, ligament, tendon, capsule, and fascia. Fascia. Mechanoreceptors. Mechanoreceptors are specialized neural receptors embedded in connective tissue that convert mechanical distortions of the tissue into neural codes to be conveyed to the central nervous system. Tissue distortion from elongation, compression, traction, or tension triggers an electrical charge across the membrane that generates neural impulses sent to the central nervous system. Impulses from peripheral mechanoreceptors are sent to the central nervous system through neurons specific to each sensation. Types of peripheral mechanism. Kinesthesia, conscious awareness of joint movement and joint position sense that results from proprioceptive input sent to the central nervous system. Kinesthesia, conscious awareness of joint movement and joint position sense that results from proprioceptive input sent to the central nervous system. Types of peripheral mechanoreceptors. Skin receptors. Joint rotation causes the skin to stretch on one side and relax on the other side. The sensory afferent neurons that detect skin stretching supply information about joint rotation. Cutaneous and proprioceptive afferents. Cutaneous and proprioceptive afferents transmit signals about joint motion to the central nervous system. Muscle mechanoreceptors. Joints move when muscle tension overcomes resistance. When a joint movement occurs, some muscles are shortened and others are lengthened. Muscle sensory afferents provide unidirectional signals of joint movement through information about each muscle's length and tension produced. These signals from the muscle mechanoreceptors tell the central nervous system about joint movement and position. When a muscle tenses around a joint, it increases the stress sensitivity of the muscle spindle, which dramatically enhances proprioception at the joint. When a muscle tenses around a joint, it increases the stretch sensitivity of the muscle spindle, which dramatically enhances proprioception at the joint level. Appropriate activation of muscle receptors during sports performance training creates maximum joint stabilization and sensory input to the central nervous system. This enhances neuromuscular efficiency and may prevent injury. The two primary muscle mechanoreceptors are the muscle spindles and the Golgi tendon organs. The two primary muscle mechanoreceptors are the muscle spindles and the Golgi tendon organs. The muscle spindle, an intrafusal muscle fiber, is a complex proprioceptive organ located in series within the muscle fibers, the extrafusal muscle fibers. The muscle spindle has both sensory and motor innervation. Muscle spindle has both sensory and motor innervation. Sensory information regarding the length of the muscle and the rate of change in length is transmitted to the central nervous system by the muscle spindle. The muscle spindle also contains contractile fibers controlled by small gamma motor neurons from the spinal cord. The motor neuron that controls muscle contractions is an alpha motor neuron. The motor neuron that controls muscle contraction is an alpha motor neuron. The muscle spindle also contains contractile fibers controlled by small gamma motor neurons from the spinal cord. The motor neuron that controls muscle contraction is an alpha motor neuron. When stretching activates the muscle spindle, a sensory response is evoked and transmitted to the spinal cord, which in turn sends impulses back to the muscle. This produces a quick contraction of the agonist and synergistic muscle fibers and causes reciprocal inhibition of the agonist muscle fibers. The strength of the muscle spindle response is determined by the rate of stretch. The faster the stretch is applied, the greater the firing frequency of the muscle spindle, and the greater the resultant reflexive muscle contraction. This co-activation of muscle spindle and extrafusal muscle fibers allows for continuous motor monitoring of the length and the rate of change in length of the originating muscle. This co-activation of the muscle spindle and extrafusal muscle fibers allows for continuous monitoring of the length and rate of change in length of the originating muscle. This allows the muscle spindle to remain under tension and provides sensory information about the length and its rate of change in the muscle, even after the muscle has been shortened. This improves the excitability and sensitivity of the central nervous system. Memory tip, page 247. Activation of muscle spindles causes a contraction of agonist and synergist. This can be remembered by thinking about the muscle part of muscle spindles. Name: muscle contract. Muscle spindles cause a contraction. Golgi tendon organ produce an opposite response when they are excited by inhibiting muscle contraction. So Golgi tendon organ produce an opposite response when they are excited by inhibiting muscle contraction. So they inhibit. Joint mechanoreceptors. Okay. The GTO is a muscle mechanoreceptor located at the musculotendinous junction in series with the extrafusal muscle fibers. See figure 411 in chapter 4. The Golgi tendon organ is primarily sensitive to tension development and rate of tension development in skeletal muscle. The Golgi tendon organ has an inhibitory effect on the skeletal muscle. The more tension produced by the muscle, the greater the frequency impulse from the Golgi tendon to the central nervous system, leading to reciprocal inhibition of the alpha motor neurons, of the agonist and synergist, thereby limiting force production. Research postulates the GTO functions as a protective mechanism to prevent overcontraction of the muscle. Joint mechanoreceptors. Joint rotation or deformation stretches this joint capsule on one side of the joint and may also compress it against the underlying bone, with structures on the contralateral side of the joint correspondingly unloaded. Joint rotation or deformation stretches the joint capsule on one side of the joint and may also compress it against the underlying bone, with structures on the contralateral side of the joint correspondingly unloaded. Ligamentous structures may also be loaded during joint rotation. There are several types of joint receptors. Ruffian afferents are large, encapsulated multicellular and organ structures located within the collagenous network of the joint fibrous capsule. These receptors are slowly adapting sensory neurons that continue to discharge information as long as mechanical stimulus is present. Ruffian afferents, joint definition, Ruffian afferents, they're joint receptors that are mechanically sensitive to tissue stress, that are activated during extremes of extension and rotation. These receptors are mechanically sensitive to tissue stress, activated during extremes of extension and rotation. They are generally considered to be the limit detectors of motion. Ruffian afferents, Ruffian limiters, Ruffian afferents, limiters. Passiniform afferents are large, cylindrical, thinly encapsulated, multicellular end organ structures. These receptors are widely distributed around the joint capsule and surrounding periarticular tissue that are mechanically sensitive to local compression and tensile loading, especially at extreme ranges of motion. They exhibit a rapid burst of impulses following stimulation, after which there is a rapid decline in the impulse rate. They exhibit a rapid burst of impulse following stimulation, after which there is a rapid decline in the impulse rate. These receptors are associated with the detection of acceleration, deceleration, or sudden changes in the deformation of the mechanoreceptors. These receptors are associated with detection of acceleration, deceleration, or sudden changes in the deformation of the mechanoreceptors. Golgi afferents are high-threshold, slowly adapting sensory receptors located in ligaments and menisci. These receptors are mechanically sensitive to tensile loads and are most sensitive at end ranges of motion. Nociceptors are small diameter afferents located primarily in articular tissue and are sensitive to mechanical deformation and pain. The sensory receptors lack directional specificity, so optimum stimulation includes abnormal rotation, deformation, or chemical changes. Close.